Okay, cool. So thank you all again for coming to the second day of the ABC Not in Svalbard workshop. Today we have the same structure as yesterday, a few talks here in Australia at the Australian Mirror, and then we're going to kick over to the Grenoble Mirror, although half the speakers are actually still in Australia. So yay for us. Today we're going to start off talking. Anthony's going to present some of his work on combined inference for states and global parameters in ABC. And then Jacob's going to go ahead and move on after that. So you guys got 25 minutes and we'll open floor for 5 for questions. Any questions before we get started?
Nope.
Great. Let's go ahead and get started. Ace, take it away, mate.
Okay. This is work I did with Pierre, Kerry, and Chris. So as David said, it's for problems where you're interested in inference with 2 types of parameters. So there's the parameters that exist on a time index, and in the normal terminology we call them states, and then there's parameters that don't that stay fixed. We call them fixed parameters or just parameters. So this is something that comes up, but there are often Bayesians who don't like the idea or the terminology of fixed parameters. But personally, I think if it's unknown, if it's an unknown parameter, it's perfectly 100% Bayesian to say that it's a fixed but unknown parameter. So anyway, it's one of my favorite rants. So we have 2 types of parameters: one parameter that really does move around, and one parameter that doesn't. But we don't know either of them, and we're trying to perform inference at the same time, and we have observations on the same time index as the state. And believe it or not, there's already a universe of methods for performing state-space inference, but typically they don't perform inference on the fixed parameters at the same time. And given that the dimensionality of the fixed parameters is usually much lower than the set of all states that you're trying to perform inference on. What kind of surprised me is that once you try to do inference on these fixed parameters at the same time as this time index, this actually adds quite a large degree of complexity to the inference problem, even though these parameters are not moving at all. Okay, starting from fixed parameters, obviously here we all understand the concept of Bayesian inference, but to fixed notation. And we've got a variety of methods for performing inference on fixed parameters: Monte Carlo, Markov chain Monte Carlo, sequential Monte Carlo, ABC. Here to talk about ABC. We all know what ABC is. Drawing parameters and accepting those that where the distance is below some threshold is the most straightforward and intuitive version of ABC. And there's a whole bunch of ABC samplers, as we know, and these mirror the samplers that exist in the likelihood-based inference. So it's Markov chain Monte Carlo ABC, sequential Monte Carlo ABC, replenishment ABC, simulated annealing ABC, etc., etc. But then we come to state-space models, and so in a state-space model, typically the they have their own type of notation. Where here, okay, so here the parameter on the time index, which we call the state, is x of t, right? And in a typical algorithm for performing state space inference, such as a particle filter, this fixed parameter here is assumed to be known, and so we're only really performing inference on this state, and the state, the value of the state determines this distribution of observations y. So we're using y to infer x, and x is moving around according to theta, but what y is distributed also depending on theta. But in the conventional state space model, we assume we know theta, and so anyway, there are already particle filters that exist for this problem, and so in a particle filter, basically we're proposing an ensemble of states that we move according to whether or not they generate observations with high likelihoods. For the data here, our likelihood is G for the observations of Y given the state. Okay, and so and to make that, to turn this into a likelihood-free particle filter, we could simply replace this likelihood here with an indicator function depending on whether the distance is less than some epsilon, which is the most obvious thing to do. The only issue is that you've got this epsilon that depends. You've got to supply a vector of epsilons, and that's so that leads to a degree of tuning that you'd rather avoid. Okay, but we've got to zoom out a bit, because we're still, at the same time as we're trying to infer the state, we're also inferring the fixed parameters. And for this purpose, the SMC squared algorithm was developed, and SMC squared stands for sequential Monte Carlo squared. This was developed by Chopin et al. In 2013. But basically the idea is that we propose a whole set of fixed parameters, and then associated with each fixed parameter is a set of proposals of the state, and then those state proposals are forward simulated. Well, they have their own particle filters, but then the issue that arises is that we run into particle degeneracy, because one of the parameters will have a much higher posterior density than the others, and so at some point you need to rejuvenate the theta, but then you have to run the whole thing again. Right. And in that way, you can generate new fixed parameter proposals. Okay, and so and so to turn this into a likelihood-free algorithm, we do the same as we did before. That is, we replace the likelihood of y, sorry, with the distance, right? And so that's that helps us. So that that gives us a particle filter for x, right? And then, well, what it does is, so it means that associated with each fixed parameter is a whole set of state parameter proposals, and each of those state parameter proposals at each time step has a whole set of distances, right? And then, and what we do here is we say, well, because we don't want to fix the epsilon beforehand, we look at all these epsilons, and then we say, which epsilon can we choose such that this sum is greater than our acceptance probability. And so this is basically the amount of distances that are less than this epsilon, right? And it's weighted with this z, because z is the weight that we're given each fixed parameter proposal, right? Because as you run it, some of the fixed parameter proposals have a lot more weight than the others, and so you don't want to just take all the epsilons, sorry, all the distances, and then say, well, what's the fifth quantile distance? Because that'll mean that you're looking at a lot of parameters that don't have a high weight, and so you just got to weight. You've got to weight the epsilon, right? Weight the distance, and so okay, that's fine, right? But then when you rejuvenate these theta, you've got to be careful, because so even though we have this method for choosing epsilon, we've got to make sure that once we regenerate these theta and we compare them with the theta proposals we already have, we have to make sure that we're making a fair comparison. And so what that means is that we've got to use the epsilons that we originally computed automatically, and we've got to remember those and feed them back in when we do the rejuvenation. So that means that we're comparing the same approximate posterior. So we tried this out with a few examples. I'll show two here. We've got a skewed normal distribution. This is a contrived example we thought of. So the state is moving around normally, and then the observations are skewed normal IID on the time index. And so here we've got the true state in red, and we've got our prediction intervals in black. Sorry, that should say black. Yeah. And then we've got, so the red here is the true fixed parameter, and these are our posterior distributions. And we've got a second example, and it's a Hawkes process. and here's our state inference. So that the red is the true state, and the thick black is the median, and with the prediction intervals. And here we've got the fixed parameter, the posterior distributions. And so, okay, so the advantage here is that we've got a likelihood-free algorithm that performs state and fixed parameter inference that doesn't have any tuning on the time index. So there's only the tuning parameters do not increase with the amount of time that you need to perform inference on. And so we've got a preprint archive here. Thank you.
Thanks, Ace. That was well timed. I'm going to go and open the floor to questions. We have a few minutes for questions.
Are we able to see everyone who's there?
I can change it.
Yeah,
Yes.
just change so we can see. I think that's good.
Side by side gallery.
Yeah.
Is that good?
Yeah, yeah. Oh, that's good.
I guess I have a question. Well, I'm a bit curious if you go back to where you have your posteriors and the true parameter estimates. So I was just a bit curious here to see what the exact posteriors would look like, or at least in the state space model where you look at a measurement equation that's skewed normal, where you could still do the particle, the pseudo-marginal metropolis hasting algorithm. So I was just curious how that would compare to the exact posterior.
We've got results like that. Yeah. So we have a stochastic volatility model that we were able to get the likelihood, well, the true posterior. I don't know if this is helpful, but sorry, I'll just need to switch to my other screen to show it. Okay.
Oh, cool.
Yeah. If that's I don't know if that's helpful. You just have to. Yeah.
Well, that looks pretty
Yeah.
accurate. About you buy another one. That's an interesting one.
Yeah. I guess these other ones weren't the best ones to show. Should have gone with this one, right?
That's a good question. Can I ask also, have you done any comparison with other methods that are available, including some by Jasra and his colleagues, and some stuff that we've done as well, for a state space modeling within intractable likelihoods, ABC-based state space modeling. So there are other methods around. So we wondered whether you had done any comparison with those in terms, and again, in terms of how accurately they pick up the exact posterior when you can produce that.
No, but I should definitely do that. Yes. Is that parameter and state at the same time?
Yeah.
So certainly the Jasra stuff is, yeah. The stuff we have in JCGS is more focused on the global parameters. We don't really consider inference on the states. It's a byproduct, and it's not nearly as accurate. So, but the Jasra stuff, if I recall correctly, is specifically targeting states. So forget exactly where it was published. Might be CompStat. Don't know. You can yeah.
You'd find it.
Yes.
Okay. Thank you. Thanks.
Do we have any other questions from the floor? So then I'll go ahead and ask a question. So can you go back to the plot where you have the estimated state transition, I guess it's not the transitions, the path and the exact comparison again, do you mind?
Yeah. Okay.
Yeah, right there, cool.
Yeah.
I guess one thing I would say here is like, it seems to be, so red is the estimate, right?
Yeah.
So it seems to be that you're underestimating pretty consistently the maximal like spikes in the Hawkes state. Is that a function, do you know, of the resulting parameter inference in the Hawkes process, or how are you consistently underestimating that?
I think we're consistently overestimating. So okay, the red is the true.
Oh, sorry. Well, then backwards. Okay,
Yeah.
backwards. Yeah.
Yeah. So
My guess, I guess what I'm saying is like if I remember correctly, like the Hawkes process is parameter driven, and it's pretty touchy depending on how those parameter values are. So I would guess like if your posteriors aren't exact, that you could easily under or overestimate states there. Is that possibly what's happening here?
So yeah, the Hawkes process is quite tricky because the way we've framed it is that the state is the baseline. So it's like what is it? So
It's a point process, isn't it?
yeah. So that this okay. So that this is kind of a little bit outside of what I was saying, because it's the Hawkes process here. Your observation actually, your y of t depends on your previous y as well, because it's self-exciting.
Mm-hmm.
So here I said that the state is like what's it called, the baseline. Sorry, what? It's like a
conditional intensity function, perhaps.
It's the Poisson process that it moves with time for me. Yeah.
Okay.
Does that make sense?
Yeah, it does. Yeah.
Yeah. And then but yeah, it's quite touchy because it's got to move. It's remembering the observation as well as the state. But yeah, sorry, I don't have a good answer for that.
What is the hi, I'm here without the cat, but I'll get the cat in a minute. What is this? Can you put up the observation and state transition equations?
Yeah. Right.
Okay, so
sorry, I'm just finding them in the paper. Okay, sorry. Okay, Hawkes first. Okay.
Okay, so.
Yeah.
I'm getting quite excited about this, but
Self-excited.
so yeah, no, don't say that. I'll get pulled off the air for that.
Okay, so
what-
that the state transition is normal, right?
yeah,
Okay. And then that in and this is the Poisson process here, and it,
Yeah.
it depends on this state, right? Sorry, I didn't realize people would be so interested in it. Okay, and we have a set of
what was that, Gail?
No, I'm just saying that I'm teasing, because I know we're a bit muffled.
I'm gonna ask
Yes.
actually that we maybe take
Yeah.
this
Off-
offline a bit,
offline.
actually, and go ahead and move on to the
Yeah,
next
yeah.
speaker. Is that
okay,
okay,
yeah,
guys?
that's fair.
Okay, so what's your mobile number so I can just call now?
Well, just give him a call on Zoom on another channel, Robert.
Chat.
Anyway, I'm gonna go ahead and thank Anthony for his talk, and then
Thank you.
we'll go ahead and